Hi folks, it's the moment you've been waiting for. I know you've been wondering, hey, when can we start doing stoichiometry with our gases? And the time has finally come. Avogadro, who gave us Avogadro's number, kind of the number of moles of a number of particles in a mole, also had gave us an important value that we use in when measuring gases. He noticed that if temperature and pressure are held constant, then equal volumes of gases contain equal numbers of moles. Equal volumes of gases contain equal numbers of moles. This is true for all gases, whether it's a light gas like hydrogen gas, which just has a molar mass of 2.02 grams per mole, or whether it's a much heavier gas like oxygen gas that has a molar mass of 32 grams per mole. They all take up the same amount of space. And this has to do with the fact, what we learned with the kinetic molecular theory, that there's kind of more empty space between particles than the size of the particles themselves. There's a lot more empty space in a gas than there is particle. We ignore the size of the particle. We ignore the volume of the particle. So remember that the coefficients in a balanced equation always give you a mole ratio. Always tells you how many moles of one substance you have, you need to react with moles of another substance. When you're talking about gases, because of Avogadro's principle here, this also means that the coefficients give you a volume ratio. If you're talking about gases, you get a volume ratio by looking at a balanced equation. So here's an example. We know from the last module that if we have this balanced equation, it means that we have 1 mole of hydrogen reacting with 1 mole of chlorine to make 2 moles of hydrogen chloride gas. But because these are all gases, we can actually make a comment about their volumes, because Avogadro said that all gases take up the same amount of space, the same volume per mole. So I could say that 1 liter of hydrogen gas reacts with 1 liter of chlorine gas to make 2 liters of hydrogen chloride. Or I could say 1 milliliter of hydrogen gas reacts with 1 milliliter of chlorine gas to make 2 milliliters of hydrogen chloride gas. It doesn't matter what units for volume I use, so long as I'm consistent. And you can see this kind of consistent relationship of 1 to 1 to 2. This only works for gases. Don't try doing it with masses, but it's a convenient relationship when you are measuring volumes of gas. So let's see how we use this relationship to solve a problem. How many liters of ammonia will be produced from 2 liters of hydrogen gas under constant pressure and temperature conditions? So temperature and pressure are not changing. So we just have to worry about the number of moles. And so if we're starting with 2.0 liters of hydrogen gas, the first thing I need to do is figure out what my balanced equation is. I'm making ammonia, which is nitrogen trihydride, so NH3, and I'm reacting hydrogen gas and nitrogen gas. Hydrogen gas and nitrogen gas. To balance this, I've got a balanced equation here. And these are all gases. And my known value is the hydrogen gas. I know I've got 2.0 liters of nitrogen gas, and I want to know how many liters of nitrogen trihydride can I make. My known and my unknown. So we've had lots of practice with this now. I need a conversion factor that gets rid of liters of hydrogen and brings in liters of ammonia or nitrogen trihydride. And I get that from the mole-mole ratio in the balanced equation. Because this is gases, this works. I get rid of, let's see, 3 is the number next to hydrogen, and 2 is the number next to ammonia. So I've got 2 times 2 divided by 3, and that gives me, as my answer, 1.33333333, but I need to report my final answer to 2 significant figures. So my final answer is 1.3 liters of nitrogen trihydride. So 1 mole ratio converted to a liter ratio, because we're dealing solely with gases, gives us the answer we need here. Let's do one more example. If we start with 500 milliliters of carbon monoxide, this is our known. I want to know what volume of oxygen is needed. This is my unknown. Again, I need a balanced equation. I've got oxygen producing carbon monoxide in a synthesis reaction. So my other reactant must be carbon. This is a synthesis reaction with one product, but I need to think about what elements come together to make that one product. Carbon is a solid, so I can't use our new trick on that material, but oxygen and carbon monoxide are gases, and those are the 2 substances I'm asking about. Carbon monoxide, I want to have 500 milliliters of it, and I need to know how much oxygen is required. So to do the calculation, I start with my 500 milliliters of carbon monoxide, and I want to think of units that will get rid, or a conversion factor that gets rid of milliliters of carbon monoxide and brings in milliliters of oxygen. According to this, oh, it is not yet balanced, my apologies. I need 2 carbons to make 2 carbon monoxides. So I've got 2 carbons, 2 carbons, 2 oxygens, 2 oxygens. It is now balanced. Using the balanced equation to get this mole-mole ratio, which we're using as a volume-volume ratio as well, I get rid of 2 mils of carbon monoxide for every 1 mil here of oxygen. So, sorry, when I say get rid of, I mean I'm getting rid of milliliters of carbon monoxide, getting rid of milliliters of carbon monoxide. And my final units are milliliters of oxygen. And doing the math, 500 times 1 divided by 2 is 250. Because I started with 3 sig figs, I should end with 3 sig figs, and so I'll put a decimal point there so that my 0 is in fact significant. So, Avogadro discovered that when he had 1 mole of a substance, or 1 mole of a gas, that it had a particular volume under standard conditions. So he gives us a new stoichiometry conversion factor. When we are at standard temperature and pressure, remember standard temperature and pressure is 273 Kelvin and 1 atmosphere of pressure. When you're at that standard temperature and pressure, 1 mole of gas has a volume of 22.4 liters. So 22.4 liters is called the standard molar volume. 1 mole is 22.4 liters. Again, as I've said, STP, standard temperature and pressure, is 273 Kelvin and 1 atmosphere of pressure. Or if you prefer to have it in kilopascals, 101.325 kilopascals. And you can use this conversion factor as to do dimensional analysis, stoichiometry involving gases, and finding out how much volume is produced. You use this when you, the previous examples, we were converting from moles of gas to moles of gas, but sometimes you're given grams of a substance instead of moles, and that's when you would use this conversion factor. So let's do an example problem using this conversion factor. What volume in liters is occupied by 0.0680 moles of hydrogen gas at STP? Notice I'm starting with hydrogen gas and I'm ending with hydrogen gas. So it's only going to take me one step, one conversion factor, to convert to or from moles. So I start with 0.0680 moles of hydrogen gas, and I want to get rid of moles of hydrogen gas and convert to liters of hydrogen gas. I know from my conversion factor that 1 mole of gas has a volume of 22.4 liters. So this is the dimensional analysis I need to do my calculation. And I get 1.5232 liters. That has too many sig figs. I just want 1, 2, 3 sig figs. Also, the 22.4 limits your sig figs as well. Rounding off our answer to 3 sig figs, we get 1.52 liters of hydrogen gas. Let's do another example of this. How many moles of oxygen are in 40.2 liters of oxygen at STP, standard temperature and pressure? So because it's STP, I know that 1 mole has a volume of 22.4 liters. So if I start with my known and try to calculate my unknown, notice we're starting and ending with oxygen, so this is only going to take me one conversion factor to convert to or from moles. If I start with 40.2 liters of oxygen, I can get rid of my liters of oxygen and convert to moles of oxygen, because 1 mole has a volume of 22.4 liters. Notice that this time I'm dividing by 22.4. So 40.2 times 1 divided by 22.4 gives me an answer on my calculator of 1.7946 moles of oxygen. But I can only report my answer to 3 sig figs, so I'm going to round off here. My number after the cutoff is less than 5, so I stick with 1.79 moles of oxygen. Let's do another example. What volume does 15 grams of nitrogen gas occupy at STP? Here I'm starting with a mass in grams as my known. But this time I'm not converting to moles or from moles either. I'm going to go all the way to a volume as my unknown. I'm starting and ending with nitrogen gas, so I don't have to convert to a different substance, but I do need to convert from grams to moles and then from moles to volume. Converting from one unit to another, you always go through moles. With these types of problems. So if I start with 15.0 grams of nitrogen gas, I want to get rid of grams of nitrogen gas. I would love to go straight to a volume in liters, but I can't. I have to go to moles first. And I know that 1 mole of nitrogen gas has a molar mass of 28.02 grams of nitrogen gas. Now, those are not the correct units for my final answer, so I want to get rid of those moles of nitrogen gas and convert to a volume. I know that 1 mole, because I'm at standard temperature and pressure, has a molar volume of 22.4 liters of nitrogen gas. I've set up my problem in a way that grams of nitrogen cancels out with grams of nitrogen, and then moles of nitrogen cancels out with moles of nitrogen, and I'm left with liters of nitrogen gas. So I've got 15.0 divided by 28.02 times 22.4, and my final answers will be liters of nitrogen. And according to my calculator, the answer is something like 11.9914. But I want to round off to 3 sig figs because the number after my cutoff is 5 or higher. I round up and I end up with 12.0 liters of nitrogen. So before we go and do a big stoichiometry problem involving this new conversion factor that we've just learned, I just wanted to refresh your memory about how we convert from mass to moles of a substance, or from particles to moles of a substance, or from volume to moles of a substance. We use conversion factors, either the molar mass or Avogadro's number, or this new conversion factor we've learned, 22.4 liters per mole, if we're talking about the volume of a gas. Then we use a mole-mole ratio from the balanced equation to convert from moles of one substance to moles of another substance. And then we use similar conversion factors from what we had at the start here to convert to mass of our new substance, or particles of our new substance, or volume of our new substance. So let's look at a problem. What volume of carbon dioxide forms from the decomposition of 1.26 moles of calcium carbonate at 1 atmosphere of pressure and 0 degrees Celsius? Firstly, you need to recognize that as being standard temperature and pressure. You need to be able to see that 1 atmosphere is standard pressure and 0 degrees Celsius is standard temperature. This tells us that 1.26 moles of calcium carbonate is decomposing, so we start with the calcium carbonate decomposing, and we're producing carbon dioxide, but the problem tells us that calcium oxide is also formed. So how do we balance this equation? Well, it's actually already balanced. We have 1 calcium, 1 calcium, 1 carbon, 1 carbon, 3 oxygens, and 2 plus 1 is 3 oxygens. So it's already balanced. And we are starting with our known value of 1.26 moles of calcium carbonate. I'm trying to get to my unknown value of the volume of carbon dioxide. So volume of carbon dioxide, I've got a different chemical substance here. So I'm starting with moles, and then I have to convert to a different substance, and then I have to convert to volume. I'm starting with moles, so it doesn't take me any steps to convert to moles because I'm already at moles. So I can go straight away to just converting to moles of my new substance. I can get rid of moles of calcium carbonate and convert to moles of carbon dioxide. And then I don't want moles of carbon dioxide as my final answer. I want to get rid of moles of carbon dioxide and convert to liters of carbon dioxide. So if I think about what units to fill in, I use my mole-mole ratio from the balanced equation. There's 1 mole of calcium carbonate for every 1 mole of carbon dioxide. And then I want to think of the conversion factor that lets me convert from moles to liters of a gas, which is 22.4 liters per mole. Before I do the math, I should check my units. Moles of calcium carbonate cancel out with moles of calcium carbonate. Moles of carbon dioxide cancel out with moles of carbon dioxide. So I'm left with liters of carbon dioxide. And when I do the math, I get 28.224, but I need to round that off to 3 sig figs, and therefore I get as my final answer 28.2 liters of carbon dioxide.